sure. Oh wait, almost. Oh, I hear the background noise. Oh, sounds like we're good. They have no way of putting your, here, I tell you what, now the chair doesn't go down that low. And the other chair's too short, so. Okay, so we're back over doing these. And you could kind of ignore those. But if you look back at the lecture last time, you realize all you have to come up with is R, take its derivative, take two derivatives. Usually somebody will give you the theta like 30 degrees, and then you're just looking for theta dot and theta double dot, and that's all you're doing is you're filling this out. So it's a fairly simple thing if you get those parts behind it. In other words, you look at the examples, first thing he'll head for, okay, this is a pretty mundane example because the radius doesn't change. But he looks for those three, and then somewhere he's got to look for, oh, he's going through some, what is he doing? He's going through proofs. Okay, so what he's going through is a little proof that I talked about that before, that in fact this term is actually the same, these two terms are the same, and that the tangential acceleration is nothing more than that. So I thought he was doing an actual problem there. But here's a case that be something more along the lines of what you would do. So he has radius as a function of time, takes its derivative, takes another derivative. He's saying at 1 second, what's the acceleration? Well, you come up with that, which actually you don't need explicitly in the equation. This one and this one you'll need, but you'll also need the theta dot, which he says the horizontal plane such that theta is equal to this. Okay, so he should have put a box or something to separate those two. In other words, here's your R and here's your theta. So here's your 6 things you need. Kind of remove that dot there. You need your theta, theta dot, theta double dot, R, R dot, and R double dot. And then you're just putting them in here. And then if he's asking you for the magnitude, now here he's asking for the angle, I don't know why. And then if you look at it, all you're doing is substituting in the values here, and you get your 2 components. And of course up here he's looking for the acceleration component. He does a good job about drawing it. In other words, you know, if you look at this, he's got the path going right here, and again the velocity is always tangent to this curve, the path curve, so that gives you an idea. You can almost look at this thing and tell whether it looks right. But the 300 is going in the theta direction, and then the 200 is going in the R direction, which is out away from the axis that it's rotating about. So they're fairly simple problems, except this one. This one is a tough one. Okay, and I'll tell you why it's tough. So he's asking, he has a searchlight, and this searchlight is rolling around in circles, of course. And what he's saying is rotates at a constant rate of that. So when the searchlight is here, the light itself is probably not moving that fast. But if down here it's moving super fast because it's so far away, and it just appears to look like it's moving fast. So what he did, I'm trying to shrink it. He basically put it in here, put a theta, and he's looking for the, so it's kind of like, it doesn't seem that way, but imagine you had a rod sitting here and a collar on it, and I'm not great at drawing this stuff. And you got another collar with a rod here, and this thing's rotating. So this thing's sliding down that thing as this is rotating. It's the same thing. So the distance from here to here is increasing as you're increasing theta, because it's a few seconds later it's here, and then it's here, and then it's down here. But you got to come up with the relationship between the r and the theta. So he uses, of course he uses the cosine of the angle, comes up with that, and goes through the process. This is the part that's not so fun, is taking the derivative of the secant. And you can see how much of a headache it comes. By the time you get to r double dot, it's like a pretty big headache. And then, but once you get through this headache, then you're just inserting the theta, the theta dot, the theta. You're just inserting everything. And that's what he does here. He comes up with 3 values. And so that's your focus is to find those 6 values, this, and of course back here you have theta dots equal to 4. It's constant, so theta double dots equals 0. And so he's focused, there's more often he'll focus on r than theta, because theta is a lot of times given. Then he's just plugging it in. And what's funny is, you'll get, the path of this thing, because these two have to go such that the direction is exactly that way. So at all times. And believe it or not, acceleration has to go that way too. So you'll have, here he shows a vector diagram of the radial component and then the theta component. They go together so that that's going directly to the left. Has to. And so these are pretty much straightforward. This is a time where you would use like some sort of calculus to get through these examples. Sometimes you wouldn't, because you don't have much to do there. Let's see, I think I did, this one was in the homework. I think we did that. Did we do, let me go back here and see, was I, nope. Where did it go? It was right there. Did I do, I know there was, oh, reconnection successful. Okay. God. Okay. Let me go back to where I was. Okay. So the next section actually becomes slightly a bit of relief. And it's the absolute motion between two particles. Analysis between two particles. Wait a minute. That's no. Yeah. Wait a minute. Oh, okay. But that's not the right title. Anyway, I questioned that title. Anyway, I didn't think that was the title. I thought that title was in the next section. Okay. So this is kind of a straightforward thing. You want to know how the motion of A affects the motion of B. But you have a rope that's tied between them. Now, the first assumption you have to make is the rope doesn't stretch. How do I say that? Rope doesn't stretch. So if it doesn't stretch, hey, is that the right aspect ratio up there? I guess it is. If it doesn't stretch, then that means its length remains the same. And so actually, if you're doing this, you just pick out the length, and then you have to pick yourself a datum. And the datum has to be something that's not moving. And you don't have to have the same datum for each block, or he'll call it mass or particle. So he may use the word particle. So think of that as a particle, and this is a particle. So you don't have to have the same datum to describe to set for each particle, but you have to have a fixed datum, and then you have to draw a vector to the particle or mass, and then what you have to do is come up with a label. Now in this, he always uses S, and so he's got an SA and SB. Now the reason he made this a little bit red there is because if I'm looking at the length of the rope, I'm going to call this like delta, or here I'll call it a capital delta. I'm trying to think, did I used to use a capital? I can't remember. Maybe I'll use a small one. So I'll say the length of the rope is delta plus SA plus SB. It's that simple. Now, if I want to take the derivative, I would just dot each of those. And then I could realize, okay, this length is fixed. So even if this moves up a foot, or whatever, even if they move back and forth, delete, the arrow here. Then the length that's touching this part right here is going to remain fixed, so that's going to be 0. The rope itself doesn't grow or shrink, so it's 0. So what you get is SA dot is equal to minus SB dot. Well, that makes sense because here, if you look at this thing, if this thing, I'm just saying this because this looks heavier, but it's also at a different incline. So let's say this one moves that direction. Common sense would tell you that one moves that direction. But this would be a plus SA dot. And that is a minus. It's going in the minus direction because this is the plus direction as defined by this direction. And so you just get those straight up. And so that's all you're doing here. If you look through the thing, I swear I thought this was a different title. Uh-oh. I thought this was a different title. So he's labeled it something like LCD, SA and SB, length of the thing. And he describes how, I touched it with one finger. I don't know what happened there. Okay, so then he takes the derivative and he says kind of this. Okay, now you can get something interesting here too. Another thing is you can have pulleys stuck in loops, and you can have different ropes stuck in loops too. So if you just stick to this kind of mindless approach that just says, okay, I'm just going to pick a datum, a spot that doesn't move. This doesn't move because hopefully that doesn't bounce up and down. And he's already identified this part being red, this part right here, and this part right here as being part of his delta, what I call delta. So I list the length of the rope. Well, I got 1, 2 SBs. Then I got plus this H, which this is kind of a weird number, but that's okay. He's labeled it, and it's okay. I took care of that one. Now I got to take care of that one. And I should have put down a 2 in front of this. I don't think I can do the same thing here. I can do it this way. The reason I put down 2 is because there's a length there and a length there. Now, if you take the derivative, you find out the ones that don't change are this one, and actually that one doesn't change. That one's fixed too. So technically, you could have included that H in here, but, he's given us that dimension. So, whatever. So what you find out is, you take the derivative, you'll get 2 SB dot is equal to minus SA dot. Now let's see if this makes sense. Hang on. If it makes sense, then okay, if this moves this way a foot, or we'll talk about the numbers in a minute when we do a problem or two. So if this moves to the right, which way would this move? If this moves to the right, then that makes it a plus. So let's just say that'll be a plus SA. I put in a plus SA here, and it becomes a minus. Well, if the rope goes this way, it's saying that this pulley will go up, and that makes sense. Now, on the next page, he does something interesting. Okay, look at how he just find his datum here. I think, yeah. On the next page, he does something weird. He changes how he defines his datum. Okay, hang on. Okay, remember it's any fixed location. So what he has chosen, and it's every person can do it differently. So this guy's here has chosen the datum that way. Okay, so if you work at that, you'd say the length of the rope is equal to your delta plus, and go ahead and put the H in because you might as well, plus, okay, if I look at these two distances, that distance is H minus SB. H minus SB. So think about that for a second. So the distance from here to here that distance is this H subtracting off the SB. So you do that, and you're sitting there. You might as well put it in. You have two of them. 2H minus SB. And then you got your SA down here, this distance right here with SA. Now take derivatives of it, and you'll find out the ones that don't give in. The ones that remain constant are this, 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 and this. So nothing happens out of this except if you take a time derivative. Those terms go to zero, so I'm just going to circle them and not even deal with them. And I'm going to say that if I take a time derivative, I get minus 2 SB dot, it's a dot, plus SA dot. Now what that means is SA dot is equal to 2 SB dot. Now, think about it logically, does this make sense? Okay, so let's say that again, this is I'm going at a plus level, say one meter per second or something. I don't know. It doesn't really matter what the number is. It's just at this point, it's just this is positive. If that's a positive number, then this will be a positive number. If that's a positive number, then that means pulling this to the right makes this go in that direction. If that's positive, and you get the same answer. It's just your number is the same. Your sign might be different. That's it. So now let's just go right in and do there's a lot of examples, but I'm gonna go right in and do one that, okay. See, I thought that, I got my titles mixed up. Anyway, that's together with this other one, but I'll cover it in a second. I'm just gonna go do a pulley problem. I'm going to try to find one that has, here we go. Yeah. Okay. Might as well get the words too. Okay, see here. Can I do this? I'm going to select everything and delete. Okay. And then what I do, there we go. Finish. Okay, so he says, determine the velocity of the cylinder B if the cylinder A moves downward at 4. Here, so if it moves downward at 4, the first thing you got to do is just look at the length of the rope. However, in here, I have 2 ropes. I have this rope, which is tied right here, goes up and over and stops right there. And then I have this rope, which starts here, goes down under here, across here, into that. So I actually have 2 ropes, which makes it seem more complicated, but it's actually not. So I start with L1. I guess I'll label this one as rope 1, and I'll obviously if that's 1, the other will be 2. So datums. Well, this spot right here moves. That spot right here moves. The only thing I can see that might be a good datum location is right here. I don't see any other pulley. What's going on? Oh, autofocus. Has it been doing that? Oh, shoot. How do you get stuff that's been doing that? Let's see. Settings. Let me go over here into settings. In a second. Let me see if I can. There's got to be a way. You see anything on autofocus? I'm trying to deal with the camera in the room. Come on, man. Was there one back there? Camera. But that's to record the thing. There is an autofocus button on this. Let's see. What happened? See, it's doing that. So, is it going to try to? It does. Well, crap. Okay, so what I'll try to do next time is I'll try to figure out how to connect to that thing. Because that's annoying. Sorry about that. So if I go in, I'll try to do my hand to the side as much as I can. So if I go in and look at the length of 1, I'll say, okay, I'll identify the delta. So that, this part, and this part. Actually, it sounds like a weird thing to say in class, but if you draw it up on the thing and watch it here, you get a better experience. The problem is the picture here is about 10 to 15 seconds behind what's happening in the classroom. So oh, what now? Say that again? No, it doesn't do the autofocus on the left. So it's not effective. Oh, okay. Okay. Well, the other thing. Oh, does it? Well, the other thing too is I've got a connection up there. I just haven't gone through the thing. I tried to one day to go through to set the thing up, and then I can cast this directly to that, so that this camera and all this. Yeah, so I want to get that. So I figure that either Friday morning at 8. I just found out this morning this room doesn't have a class at 8, so I can have an hour here to work on that before. I'll either do it Friday or Monday. Now I don't know what's going to happen, but apparently there's going to be a huge snowstorm. But I'm still going to live stream something. If they cut classes, I'll just do a shorter one or something. But I don't know what's going on. I just try to do what I'm supposed to do. So the red is all the deltas. So then I got to come up with a measuring thing. I've only got 2. None. So let me get rid of the word data. And I should have drawn this part first. Okay, so I have to identify several things. One, if I identify this velocity, then from looking at things, this is connected just by a rope. So the first thing I can realize is, if I find the velocity of D, then I've actually found the velocity of B. They're the same. There's nothing over here like that. So I should have written this, and should be writing this. So this block can move, and there's nothing it's attached to. It's not directly attached to a pulley above it like this one. So it has its own individual thing. And then I need to have the SD. Okay, I think at that point, I have everything there that I need, and I should have done that before. So now I need to put together my links. So from here to here will be SD. Then from here to here, oh crap, there's nothing that gives me that right off until I notice that if I take this length and subtract this length from it, that's what that distance is. In other words, if I'm actually truly looking for the distance between here and here, then just by looking at this would be SD minus SC. So I just put that in. And I'll put a parentheses around it. And then after that, I think I'll just take it back off if that's okay. Okay, so I took it back off. And now I got this little part. Okay, I should have left this on there. Took care of that one. Took care of that one. Now I got to take care of this one. Well, this one is the distance between there and there. So to me, that looks like that distance is SA minus SC. Not C, SC. Is that even showing up? Yeah. So here I got one little subsection, two little subsections, and then the third subsection. So if you look at it that way, this is the first subsection, that's the little second, and this is the third. Now, if I start gathering terms, what I end up with is L1 plus delta plus, okay, I see two SDs. I see two SCs. Two SCs. And then I see an SA. I think I did that okay. And then I take a derivative. I get, that should be equal. I get 0 is equal to SD dot minus 2SC dot plus SA dot. Did I add all those right? I think I did. If I didn't, let me know. This is one of the most uncomfortable chairs. Okay, so I'm just box that and hold on to it for 5-10 seconds. And now I have to look at the other rope. The reason being is because this rope right here, I should change the pen. So this rope, go away. Okay, this rope, I'm sorry, not that one, but this rope right here will tie the motion of D and C together. And so let me take a look at how I can deal with that and say, okay, the length of that rope, which I guess I'll call it length 2, has a different delta, but that delta is only the length up over here plus, okay, I need to know that length right there. And that length is just simply SD, and then I got to have this link, okay, SC. See if I copied that right. Now, one of the things you have to realize, okay, so hang on. Yeah. And so, first I need to write that correctly with an equal sign. Take a derivative and I get 0 is equal to SD dot plus SC dot. Now, it's just a case in point that something interesting, because if you look at this thing, what do you not know? What are the variables in here? You got SA, oops, S. There is no B, is there? Oh, well, wait a minute. B and D are the same. So SC and SD. Now, what's funny is, if you have one of them's velocity, which you do right here, then you have two unknowns. So you have two unknowns if you look at that. So it makes sense you got to have two equations. And it just so happens you have to have two rows. Because this is the dumbest thing you're going to hear me say. But if you clip this rope, what happens? I mean, what's going to happen is this pulley's going to fall, this pulley's going to fall, and it's going to be kind of just a mess. There's going to be no motion except just a collapse. So let's go ahead and put this in and find the answer here. So what do I do know? He tells me this velocity is going down. Well, this is the same direction as that vector, so that means SA dot is equal to plus 4, because they're both in the same direction. So I could do one of two things. What does he want to know? The cylinder at B. So you do want to know D. So I can take this, and what I can do is I can take SD dot equals to minus SC dot, and use that to get rid of one of the terms back here. But what I really want to do is I want to keep this one in there because I want to solve for SD. That's what he's asking me kind of for. So that means, to me, I would want to I'll do it like this. I'll take the SC and I'll stick it in here and rewrite the equation. So if I did that and rewrote the equation, I'd get 0 is equal to SD dot minus 2. Now instead of SC, you're putting in minus, which makes that a plus, 2SD plus SA. Now, that gives you those three. And then if you move those to the other side, or move this other to the other side, okay, so you got that. Now, you can drag that down and put in 4. And then you can take this, and then you'll get that. So, what I'm going to do, sorry about that, but I'm going to eat part of a cookie I didn't eat. Apparently I didn't eat enough, so as you ponder that, I'm going to take a bite and I'll get back to it in 5-6 seconds. Sorry, give me a second here. So does it make sense? So first of all, the value, you can figure out the value, but I'm more interested in the sign. In other words, this sign tells me that since SD is positive going down, it becomes negative. That means this is being drawn back up. And to me, that kind of makes sense. Because this rope, if this is going down, then the distance between here and here, add this and add this, it has to be decreasing because this distance right here is increasing. These two together have to decrease the same amount to offset it. The only way that can happen is if this thing is rolling upwards, or not rolling. I guess technically you could say it's rolling. Okay, so that's the most complicated one. I went straight for the most complicated. There is some side issues. Now, let me give you one case in point. Let me find it. Let's see if I can find it. Or if I can't find it, I can just take a problem. Like, for example, okay, this is one. This is it. Let's do this one. And then next time what I'll do is try to find the ones that are in the homework and look at those. But actually, before I copy, I'm going to make one comment. Let's say in the problem statement, well, I'll go ahead and copy it because I have it in the clipboard, and then I'm going to come back and say something about this one, because there's something that needs to be said. And this is actually pretty important because it will create a lot less work for you. Let's say instead of this, he asked the question, he said velocity didn't happen, but let's say block A moved down 4 feet. He didn't give you the velocity. He gave you that it moved a certain distance. So it moved 4 feet. How far did block B move? And in what direction? Now, when you look at this thing, I've seen people work this in these weird ways, and I keep thinking as I watch them, are you nuts or something? Because actually, if you look at this problem said, you came up with SA is equal to 4 feet per second, and then you came up with an answer that said SD is equal to minus 4/3 feet per second. And if it moved 4 feet and he didn't tell you how long it took it to do it, why don't you just assume delta T equals to 1 second? So if it took it in 1 second, then that means SA would be SA dot times the delta T. So if you look at it, it's 4 feet per second, and it took 1 second. Therefore, in 1 second, the thing moved 4 foot. Okay, and that same very 1 second, SD moved minus 4/3 feet per second times, say it took it 1 second. I mean, I made this part up, but it's totally legal. You just assume it took place in 1 second, and guess what you get? Moves up 4/3 of a foot, which is like 1 1/3. So instead of going through a strange rigmarole, just go into this concept, find the velocity, and then just make the assumption everything happens in 1 second. So that means if somebody tells you it moves, block A moved down 10 feet, I would turn around and immediately write, well, velocity at A is equal to 10 feet per second. And I'd work the problem just like that, get all the way done, and then take the 10, and then, it'll turn into, like, this part right here. This part right here will turn into plus 10. And then, then you're going to come over here and put in the, you're going to put in your plus 10 right here, and then you're going to get minus 10 over 3, and then you just multiply times 1 second. So there's no real reason to do any of those problems any different than this problem, except you make that one simple mental statement that everything occurs in 1 second. So with that, I'll move to the next one. Okay, so this is a case in which he's given you, okay, first of all, looks like I got 3 ropes. So that's lovely, stupid sort of way. So when he has a motor sitting here, he generally puts a dot on it. If he does not put a dot, put one yourself and label it. Because he's labeled it for us, that's why I picked this one. He labeled it. And so it's a good one to do this because he's helping us in that regard. So when you're looking at the length of the rope, this part of the rope is not included. But what happens is the motor is drawing it onto here and it's pulling it closer to itself. I'm guessing maybe it's letting it off. I don't know. Then I'm going to go ahead and use the same datum in SD, SC, and SB. Now, just in case, let's see. I got a rope here, goes to there. So obviously I got 3 hooks right there. Then I have a rope, goes from here, here, and then a rope that goes from here to there. So I got to deal with all 3 of those. However, they're all within the range of something that's easy to deal with. So if I just haul off and start looking at them, I'll move them from left to right. So length root of 1 is just SA. Whoop, I always like to put the delta first. Delta plus SA. So that's this distance taken care of. Well, here's an interesting thing. This is gonna seem weird, but do you need to even care about that part? And in fact, no, you don't. So in your mind, you could just take that off. And so what I took off is this part right here. So I don't even have to consider this area. And so if you go ahead and just look at that, you got this part from here to here, and that part, which are the same, which is 2 SD. Now I'm going to go ahead and take the derivative, and then I'm going to immediately do the next one. And I'll just hold on to it. Now, head off, do the next one. The next one, the next rope, is this. Whoop, hang on. This around up to here. So its length 2 is equal to a delta, which is the ones that's hanging over the pulley. The first interesting thing is this distance. And that's nothing more than SC minus SD. And then you got this distance. And that's like SC, if I'm not, yeah, SC. That's it. So now take your derivative there. Okay, now I'll have to recognize I got a couple of those. 2 not C, but SC dot minus SD, and there you go, there's that one. And now I'm color coding them for myself. So let's look at this last rope. This last rope is here and here. So, and by the way, this block moves the same as SB, so. Okay, so I got this distance from here to here. Length 3 is equal to the delta plus, I get SB minus SC. And then I get the length that goes all the way up here, which is this SB. I'm going to get rid of all this crap on here. And so take a derivative and you get, okay, and recognizing these two are the same, 2 SB dot minus SC dot. And there you go. So now what he's told us is this. I don't like that color. He's told us this. He's told us that VA is equal to 3t squared. Now, one of the things he didn't tell us, and this is great, but did he tell us, oh, can be wound onto the drum. Okay, so this means that SA dot is equal to 3t squared. I didn't know whether he told us whether it would be wound on or let off. Now he wants to know the time it takes needed to lift the load 7 meters. Okay. So, again, this is a little bit weird, but here we go. I can just take the SA, shove it in here. Okay, then I'll have an SD out of that. And then I can shove it into here. And out of that, I'll get SC, and I can shove it into here. And I get out SB. Now, or I can just shove them all together. So, in fact, I can work my way from A all the way to B by going through all 3 equations. So let me just do that real quick. So if I grab the first one, 3t squared, or here, I'm grabbing this equation and this one together, and I'm saying, I'm putting in the SA in there, and then I'm saying 2 SD. So then that means SD, that's supposed to be D dot. Move this over, and then I get 3/2 t squared. Well, now I'm going to take that and shove it in the next equation. The other equation being 2 SC dot minus what is supposed to be SD, which becomes, I'll make it as a minus 3/2 t squared. So in fact, this is here. So I get this becomes a plus, I move it to the other side, and I get 2 SC dot is equal to minus 3/2 t squared. Take that 2 back out again, and I get SC dot is equal to minus 3/4 t squared. Now I got SC, I shove it in with this, and that equation, and I'll say 0 equals to S, or 2 times SB minus, in brackets, what the SC is, minus 3/4 t squared. Now, sit there and say SB dot is equal to, well, I'll take the 2 first. Plus, it becomes minus, becomes plus, move it to the other side, it becomes minus 3/4 t squared, or, why am I writing S? supposed to be D, equals to 3/8. Is that right? He said, oh crap, we overdid our term. But anyway, we should go. Okay, so SB, I didn't even do the word of the day, did I? I can do it real quick. I'll do it real quick. I'll try to see if I can get in. I'm not sure I can get in that quick. At least it'll be there in the. I like to do it myself because then I get it gets put in the record too that I was there. Okay, this is dynamics. There is dynamics. Here I am. Let's see. Boat. How about that? All right. So I'll try to come and try to see if I can fix that thing to mesh with it later. I don't know.